Why is it so important to understand block size? Why is it so important to be able to figure out the subnet ID and the usable addresses within those subnets? Well, if I asked you right now, are all of these devices addressed appropriately so they can communicate with each other? You can't guess yes or no. You have to know, without a doubt, exactly what the answer to that is. So it's either you are 100% saying yes or you are 100% saying no. So how do we figure that out? Well, we're going to base it on what? We're going to base it on block size. That's right. We're going to base it on block size to figure out our answer. So I need to figure out if 10.1.1.1 and 10.1.1.2 are actually in the same subnet. And you might look at that and say, well, yeah, the addresses are so close together. Of course they are. No, that's the thing. The addresses may be really close together, but still within different subnets. So always be very, very careful when answering a question as such. You must figure out what are the true addresses in each subnet that are usable. Because one of these might be a subnet ID. One of these might be a directed broadcast address. In the real world, although you couldn't assign those to end stations or routers, well, on a piece of paper, on a document, on an exam, that could be written down. And that would be the reason why communication is not happening. So you have to be addressed appropriately for communication to occur. So let's go ahead right now and focus on how we can identify whether these devices are addressed appropriately or not. It's all about block size. So what we're going to deal with here, we're going to deal with our /30 here. So with a /30, I want to figure out the usable addresses when we have a /30. So with a /30, we have 8 bits in the first octet, 8 bits in the second octet, 8 bits in the third octet, and then 6 bits in the fourth octet, because we have 8 plus 8 plus 8, that's 24, 25, 26, 27, 28, 29, 30. So we have 24, 25, 26, 27, 28, 29, 30, 31, 32. So what is the value of this bit position in decimal? Well, that happens to be 4. Because this would be a value of 1. This is a value of 2. This is a value of 4. And then we have 8, 16, 32, 64, 128. So what we're doing here is we're figuring out what we're counting by. So we're counting by 4 in the fourth octet. Okay, so now that I know I'm counting by 4 in the fourth octet, we can figure out the subnet IDs. So the first subnet would actually be 10.1.1.0/30. And what would the second octet be? Well, we're counting by 4 in the fourth octet. So the second subnet would be .4/30. And then we'd have .8/30. So when you now analyze the results of the block size, we can see that our value of .1 belongs to the first subnet. We can see that the value of .2 also belongs to the first subnet. So the subnet ID for the first subnet is .0. The directed broadcast address for the first subnet would be .3. So the usable addresses are .1 and .2. So these are addressed perfectly fine. Let's analyze the second one. Again, it's a /30. So we already know that with a /30, we're counting by 4 in the fourth octet. So my first subnet here would be 172.16.1.0/30. And then we'd have 1.4/30. So .1 falls in the first subnet. .2 also falls in the first subnet. So we are addressed appropriately here as well. Now let's shift our attention to our bottom example here. When I look at the bottom example, it's a little more complicated because we have way more devices in this particular example. So although we have more devices, we're still dealing with block size. So in this case, we're dealing with a /28. So let's figure out the block size of a /28. So the /28, I have 8 in the first octet, 8 in the second octet, 8 in the third octet, so 8 bits. So 8, 8, 8, that's 24 bits, 24. Fourth octet now, 25, 26, 27, 28, 29, 30, 31, 32. All right. So 28 ones, as we can see here. What is the value of this bit position? Well, we'd have 128, 64, 32. There's our 16. So we're counting by 16 in what? In the fourth. Counting by 16 in the fourth. So now let's work out our subnet IDs. So our first value here, we can see we're dealing with 192.168.1. So that would be by default a /24 as its classful address. So our first subnet would have been 192.168.1.0/28. And then we're counting by 16 in the fourth. So the second one's 192.168.1.16/28. And then the next one would be .32/28, and so on and so forth. Now, do I have to keep writing them down? Well, it all depends. What are the addresses that we see on the slide? Well, .1, we know that falls within the first subnet. So first subnet. .10, ooh, that still falls within the first subnet, so we're good there. .11, that's in the first subnet. .13, that's in the first subnet. .3, that's in the first subnet. .12, that's in the first subnet. So everybody off this router interface has to be in the same subnet, in the same local area network, in the same broadcast domain. And by analyzing the block size and ultimately determining our subnet IDs, we can confirm that all of these addresses are within the first subnet. Therefore, they are addressed appropriately. But we still must check to make sure that nobody has the subnet ID assigned to them of 1.0, which none of them do. And none of them have the directed broadcast address assigned to them. So to figure out the directed broadcast address, we take the next subnet. So in this case, it starts off at .16. So subtract 1 from that. The directed broadcast address is .15 for the first subnet. So the directed broadcast address is 192.168.1.15 for this first subnet. Does anybody have .15? No, not at all. So as a result of that, everybody is addressed appropriately in these scenarios.